and get started now. It's a real pleasure to introduce Joel Spruck from Johns Hopkins University. And his talk today is entitled A Personal Tribute to Louis Nirenberg, February 28th, 1925 to January 26th, 2020. Joel?
Okay, thanks very much. Okay, so this in some sense is an overdue talk because Louis passed away last year, just short of his 95th birthday. And it's of course also hard to give a talk, a remembrance and a tribute to someone so famous and so well liked and so well known by the whole world. But I decided I'm going to, I basically grew up with Louis Nirenberg. I was a Courant instructor. That was more or less the beginning of my career. So I've known him my whole mathematical life. So, so the preface of my talk is I met, California meets New York. I met Louis in person in 1972. I actually had some correspondence with him. I might have seen him like for 5 minutes in California once, but I actually submitted, I didn't know, I realized this was very odd that Louis was actually a editor for JDG for a few years. And I actually submitted a short 2-3-page paper to him, which he, it's called On the Radius of the Smallest Ball Containing a Compact Manifold of Curvature Greater than or equal to 1. And I sent it to him because I knew he'd be interested in the problem, and he promptly gave it to Gene Calabi to referee. So that was actually my first contact with Louis. Then I became a Courant instructor after my PhD at Stanford. And of course, Louis was already a celebrated mathematician, and to me, as a postdoc, was a giant figure. He was born in Canada, in Hamilton, and grew up in Montreal, but he already was a suave New Yorker. He seemed like he was there his whole life. And I was born in Brooklyn, New York. And so this postdoc at Courant was a return home for me. So I have posted here pictures of myself and Louis that are about contemporaneous. So as you can see, I had been perhaps overly influenced by my time at Stanford in the late 60s, by the anti-war and hippie culture and political activism.
I remember those days, Joel, when you were a graduate student.
That's right, Denny. That's right, exactly. But Louis accepted me and welcomed me with no hesitation at all. And I was amazed at that. He really was a great mentor to me. I'm going to in this talk not talk about his the period of work that's roughly started. His paper started appearing around 1953, and he, in the 20-year period from 53 to 73, he produced an incredible stream of work, starting with, he got his PhD in 49, but his papers started appearing in 53, starting with his thesis, solving the classical Weil and Minkowski problems in the smooth category. Since this is the Geometry Festival, I'll mostly talk about work inspired by geometric ideas. And I'm going to give some historical background to his collaborations and how things got to be in some sense. I have to, of course, I have to apologize. I'm only going to talk about a few select things. and Louis collaborated with so many people, so I apologize for omitting so many results. In the last 25 years, many of his collaborations were with Yanyan Li, one of his most devoted and brilliant students. But as I say, fortunately, there have been many, many celebrations of his work. Over his lifetime, he received many, many prizes and awards. The last one was the Abel Prize in 2015. And so there's many remembrances and celebrations already. Okay, so I want to start, one of his most famous early works of hardcore PDE was his work with Agman and Douglas, famous Agman Douglas Nirenberg papers. They introduced a very, very general, non-standard notion of an elliptic system. And it's really, really hard to understand and mysterious. And I want to give two, even though I'm going to talk about geometry, I want to start with, since he was such a hardcore analyst, I want to start with two examples of what we call free boundary regularity that is contained in a paper of Louis and David Kindler and myself. The first example is due to Hans Levy. Louis really studied, was a great admirer of Levy and really knew his work very well. Of course, he had worked on the Weyl problem and Manjampia equations in 2 dimensions, with analytic data. So the problem of Levy, and Levy was a master at constructing amazing odd examples and reflection methods and things like that. So here's the Levy example. So Levy's example is this one. You have a harmonic function and you have another function. For example, lambda might be a constant here. So a solution of an eigenvalue equation, Laplacian v plus lambda v equals 0. And so the picture is like this, that this is a local thing. You have a domain here, omega, and the has partially flat boundary. And U and V share Cauchy data on the boundary. Okay, so what does, and so Levy proved in 2 dimensions that U and V extend analytically across the boundary. So why is this surprising? Well, it looks like U and V have nothing to do with each other. You have just disjoint equations. They just have the same Cauchy. They just happen to have the same Cauchy data. So why should they have? Why should they extend across the boundary? It looks like they're independent. So this theorem is very odd. So in terms of PDE, we say this elliptic system here, so it looks like an elliptic system, it is not coercive in the sense its boundary conditions don't make it analytic up to the boundary. So it appears that way at first glance. So Levy proved in 2 dimensions, and in this paper with Louis and David Kindler, we show that there is coercivity using this mysterious Agman-Douglas-Nirenberg work. So to show that coercivity is present, we rewrite we shuffle the unknowns and introduce what we call a splitting. We let W be U minus V, and then rewrite the system in terms of U and W. So that way we get harmonic function U, and then we get Laplacian W plus lambda W plus U equals 0. And now we have 0 Cauchy data for W. is our boundary conditions. Okay, so why is this odd? Well, in the Agman-Douglas-Nirenberg theory, you assign a weight, S, you assign a weight to each equation and each unknown. So the weights are, you have an integer weight to each equation. And so for example, I think I have the numbers backwards. We assign the weight S equals 0 to equation and S equal -2. So this is like S equals 0 and S equal -2. So by convention, we've normalized the weights to have maximum 0. So they're negative integers. And then you assign in this theory a weight T to each unknown. So here we have weight T sub U equal 2 and T sub W equal 4. And in this theory, the degree of, so S plus T defines the principal part, the SK plus TJ defines the principal part of the equations for U and for W. So here, the principal part, so what's weird in this Agman-Douglas theory is that the principal part of the system that I wrote down is Laplacian U equals 0 and Laplacian W plus lambda U equals 0. The U in the second equation stays. It's part of the principal symbol, principal part of that system. Because this is 4, S sub U is -2. And so S for this equation is -2. So -2 plus 4 is 2. And this is the right order for this equation. So in this theory, this is the principal part. So now the boundary conditions are coercive. Why? Well, in fact, you could in fact eliminate U entirely. If lambda is not 0, you could eliminate U entirely and write it as a fourth order equation for W, Laplacian squared W plus lower order terms. And then you have Dirichlet boundary conditions, and that's well known to be coercive. But the point of the theory is that you don't have to eliminate. You just have to check whether the weights are consistent and coercive. So this is a very odd and powerful thing. They point out in their in the first paper of Louis with Douglas, they point out that this is an oddity of their theory, that normally all the second order equations are second order. They're not, you don't have these system of weights. And in fact, this example shows the oddity of the theory that by a linear change, you change the ellipticity of the system in their setting. Nevertheless, they point out that it is true that there is some linear, you can't really destroy the ellipticity of the system by doing that. It's there and it can be recovered. So this is the first theory. Somehow Louis knew to connect this with his old papers. So this free boundary stuff was really in the late 70s, and his work on elliptic systems was in the 50s. And somehow he knew that this was applicable. The second example from this paper is a more geometric example. Consider a configuration of 3 minimal surfaces meeting along a curve that has a certain amount of regularity, C1 alpha. That's called the liquid edge. So if you do soap bubble experiments, this is one of the stable singularities that you will see in the case of meeting at equal angles. So this is in the thesis of Gene Taylor, for example. So the question, a classical question of Gene Taylor and Fred Almgren was, how smooth is this really liquid edge? This liquid edge is a free boundary. So in this example, I'm not going to go through the too much of the technicalities, but I do want to point out some novel feature of what we did. So the way to look at this in terms of PDE is to represent the three surfaces as graphs over the tangent plane to one of them. And then you project everything onto this tangent plane. When you do that, you get a situation that kind of looks like this. You have this projection of the liquid edge, and then you have two sides. Once you project into the tangent plane, and you have some origin here, and then you have two of the graphs defined on one side and one of the graphs defined on the other side. So that's a common kind of thing in free boundary theory. And then, so you have the minimal surface operator, M, acting on all the graphs is 0. I won't write the minimal surface operator. And then they all, you have U1 equal U2 equal U3 as one boundary condition. And then you have these angle boundary conditions. You can allow the angles to be non-physical. You don't have to require them to meet at 2 pi over 3. They can meet at other constant angles, and that works too. So what is unusual about this is, so we proved that using, so here we don't need the power of his Aglas-Douglas-Nirenberg theorem, but we did prove that the free boundary is analytic. So what's interesting is that Levy used Lagenda transform a lot, and what we do is introduce the so-called zeroth order Lagenda transform. So you have to introduce a new variable W to be U2 minus U1. And so we introduce a transformation in only a partial Lagenda transform, what we call the zeroth order Lagenda transform. So in the normal direction at the origin. And so let me draw you a picture here. So the picture is that here's the normal direction, and you introduce W to be U1 minus U2. And then you transform coordinates to flatten this free boundary gamma by introducing Y equal X prime W. Since U1 and U2 agree on the boundary, then W is 0 on gamma. So it maps the X space to the Y space, and it flattens the free boundary. So it maps to a domain U in Y space. Now, so the problem, we'd like to use the elliptic theory, but we don't know how. We have U3 defined over here on this side. So somehow we have to do some sort of reflection across. And so there's a simple way. So let me go back for a minute. This partial Legendre transform has very, very nice properties. Namely, has an inverse function, psi. So the inverse map is x is y prime psi of y. And we don't know psi, but we know it exists because this is non-degenerate transformation. And you can calculate all the derivatives, like the first derivative of w in the normal direction is 1 over psi n, and the tangential derivative w alpha is minus psi alpha over psi n. So this is sort of like classical Legendre transform. And then you can calculate that ddxn, how it transforms like 1 over psi n ddyn. ddx alpha is ddy alpha, and then you have a minus psi alpha over psi n ddyn. And now you can just, instead of knowing any kind of fancy reflection, you can just choose a reflection. Namely, you just choose a reflection mapping to be y prime psi minus a big constant times yn. So that this, where the constant is so big that it's bigger than the gradient psi, that forces it to map u to the opposite side. So once you do that, with this reflection mapping, now you can write everything back to an elliptic system now that's defined all in one side. So you have psi, so you have so you can pull back u1 becomes a phi 1, you have a phi 2, or what did I call it? I called it phi plus. So you have phi plus is u1, so you have a phi plus, a phi minus, and you have psi. And now u2 can be expressed in terms of w plus phi plus, it's just yn plus phi plus. So now you can write everything as an elliptic system in this domain U, and it turns out to be a coercive elliptic system in the sense of Agman, Douglas, Nirenberg. But the important point here is that the flexibility of this mapping, of making reflection mappings with this. So Louis was extremely clever and knowledgeable about the literature and about Levy's work. So he had the insight about how to proceed in this example. Okay, so that's all I wanted to say about hardcore PDE, but I wanted to now talk about geometry. So I want to talk about basically mean curvature and soap bubbles to start. So a central question in differential geometry has always been, classify all the soap bubbles. Classify all closed constant mean curvature surfaces, hypersurfaces in Rn plus 1 or in a special Riemannian manifold. Obviously, you need some conditions. So amazingly, the first result in this direction was proved by an Englishman, Gillette. I think he was an engineer. He proved that a star-shaped closed surface, so with the extra assumption that the surface, the constant mean curvature surface is star-shaped, in R3, he proved that it's the round sphere. A modern presentation, his proof works in Rn plus 1. A modern presentation of his proof, it goes like this, that if x is the position vector with constant mean curvature, then, and it's star-shaped, so x dot, the normal, is greater than or equal to 0. And you take delta to be the Laplace-Beltrami operator. Then you have these 4 identities. The Laplacian is minus nh times the normal. The Laplacian of the normal is minus norm a squared times the normal. And then from those two, you can calculate it follows from the first two that you can calculate the third and the fourth. The Laplacian of the position vector squared over 2 is n minus nhn, and the Laplacian of the support function x dot n is nh minus norm a squared x dot n. And then if you take the combination, if you consider the combination h absolute x squared over 2 minus x dot n, you get something, this combination norm a squared minus nh squared times the x dot n, and that's always greater than or equal to 0. So if you integrate that, you get that norm a squared is nh squared, or m is totally umbilic, so it must be the round sphere. So that was a motivating, so that's a very, very early classical, a solution of a classical problem. So to continue my story, around 1955 and 56, Heinz Hopf visited Courant in Stanford. When I was a graduate student, we went through his lectures and rewrote them, actually. So he lectured on, at Courant, I think he lectured on various topics in differential geometry in the large. And he, in both places, he presents his ingenious, well-known proof that if M is immersed of constant mean curvature and G is 0, then M is the round sphere. So but he also, for the story I want to tell, he also sketched the proof of a new result of Alexandrov. At the time, it was unpublished. A closed embedded surface in a hypersurface in Rn plus 1 of constant mean curvature is the round sphere. And he goes on to speculate that this is going to be a very, very important proof and method of proof that he introduces. And in this, in this proof is, of course, his famous method of moving planes. So in this, he introduces moving planes. And I'll get to talk about a little bit about moving planes in a minute. So Jim Sarin, so moving planes, Alexandrov, this is one instance where geometers recognized very early that this was a very powerful method. And so geometers heavily used Alexandrov's method. For example, Bill Meeks proved fantastic theorems about complete surfaces of constant mean curvature, and other people symmetry results. And so the geometers jumped on this, but the PDE people did not really. They thought it was something about geometry and they didn't use this. But Jim Sarin actually was the first person to realize this could be important in PDE. Jim Sarin I met when after Courant, I left Courant, I went to Minnesota where he was a senior professor. He was a brilliant innovator in elliptic theory, calculus of variations, fluid mechanics, and he passed away in 2012. But for the important point of my story is that he published, he was interested also a little bit in free boundary problems and capillary problems. And he considers this free boundary problem. You have a solution of Laplacian u equal -1 in a domain omega. And you have overdetermined boundary conditions where u is 0 and the normal derivative is constant on the boundary. And then he proves that the domain must be a ball, must be symmetric. And one other thing in this paper, a more physical example, is that you have a capillary tube and you have a liquid. I better, if I'm going to do that, you have a capillary tube and you have a capillary surface. And so instead of this Laplace Poisson equation, you can consider where the mean curvature of this liquid, you have a liquid and a gas, the mean curvature is proportional to the height. And then you have constant boundary condition. And instead of u nu, you would have angle boundary condition. And then the conclusion is that the tube must have been spherical tube. So the important point of this paper was that he used Alexandrov's method in the PDE context, and he developed a significant improvement of Hop's boundary point lemma. He introduced a lot of technical machinery, and he also used this continuous, he was the first, I think, to introduce this continuous sweeping use of the maximum principle. His techniques were simplified and improved later in the famous paper of Louis Nirenberg. And most importantly, so in some sense, Jim Sarin missed the bigger picture. So Jim was trying to prove from having a symmetric operator and kind of overdetermined symmetric boundary conditions that the domain was symmetric. So Louis realized that Sarin's idea could be turned around. The basic question is, when do solutions of elliptic equations inherit the symmetry of the domain? So let me, so many problems in Yang-Mills theory, in astrophysics, in reaction diffusion equations are of semi-linear form, Laplacian u plus f of u equals 0. And as such, the equations have a lot of symmetries. For example, a typical example is when f of u is a power nonlinearity, u to the alpha, and the range when alpha is less than n plus 2 over n minus 2 and bigger than or equal to 1 is called subcritical because of Sobolev embedding theorem. And the range alpha bigger than n plus 2 over n minus 2 is called supercritical. And the particular case of equality is particularly important because the equation becomes conformally invariant and is related. It's essentially the conformally flat case of the famous Yamabe problem. So first question you might ask us is, suppose you have a solution of Laplacian u plus f of u equals 0, u non-negative in the unit ball, u is 0 on the boundary, is u radially symmetric? Of course, the answer is no, unless you assume you have to, if you allow u to change sign, then you have eigenfunctions and things like that. So you have to assume positivity, you see very easily. A second question is, you can also consider a global question in Rn. Consider the equation in Rn and now throw in u greater than or equal to 0. Is u radially symmetric? The case of the Yamabe, conformally flat Yamabe equation has explicit solutions that you can write down. On the other hand, the subcritical case I proved with Gidas, if you take alpha subcritical, there are no non-trivial solutions. So there's some subtlety in this question. Also, there's a complicated, in the critical case, there's a complicated family of singular solutions that look like they blow up at a point like r to the minus n minus 2 over 2. But they may have a periodic factor psi of t, where t is minus log r. And psi satisfies a periodic translation invariant ODE. And of course, if psi is constant, you get the simplest singular solution. But that makes the classification of singular solutions very complicated. And also, what do you have to assume growth conditions? Do you have to assume something? These are all complications of the thing. So in a famous paper of Louis Nirenberg, they proved versions of solutions to both those problems. They had to assume, make assumptions along the way. So I'm not going to talk about that in some sense. I want to, one thing about Louis was, he was like a dog with a bone. He never let things go. If he just methodically worked through, if he didn't prove everything in a first paper, he would go on to a second paper and a third paper, or years later he'd come back to the problem. And but he later made substantial improvements of in a paper with Berestiki by incorporating what's called the Alexandrov maximum principle. And he was able to prove, for example, a very optimal theory that where basically if you have symmetry in one direction, like the x1 direction, then and you have the nonlinearity only has to be Lipschitz, then you inherit that symmetry. The solution, and U is non-negative, inherits the symmetry. They couldn't prove this this is actually very tricky to prove by just PDE ideas. It's very hard. So I want to explain what these ideas of Alexandrov, because I don't know that this is one, these are ideas that are very now important in fully nonlinear elliptic PDE and not so well known to geometers. So you can tell me if you know these ideas, but I want to explain Alexandrov's generalized gradient map and his Manjampia measure. So I want to just sketch this very simple but brilliant idea. So Alexandrov introduced what he called the normal mapping. Nowadays, we just call it the subdifferential. Suppose U is even just a continuous function defined in omega, a domain in Rn, a bounded domain. Then you consider the subdifferential is the set of P, which you should think of as slopes of planes. So the P's are slopes of planes, such that U of x is big. So there's a plane. So the subdifferential at x naught is the set of slopes such that you can touch from below the graph of U by this plane with slope P. So you have the graph of U. It doesn't have to be convex anything, and you can touch it. So this is the plane. So this is a plane, can be touched. We could also have, so that's his subdifferential, set of all slopes. And then you can, this may be empty, of course. And then he defines what's called the lower context set, is the set of points X in the domain for which the subdifferential of U at X is non-empty. So that's the lower context. So for example, if U is a C1 function and X is in gamma, the lower context set, then the subdifferential is just the gradient of U. And if U is C2, then and X is in the context set, then if you can contact from below by a plane, then the Hessian of U must be non-negative. It must inherit some convexity. So for example, an important example, a simple example is just take a cone. Just take a cone, take a disk of radius R and take a cone of height H. So that's our U. Then the subdifferential at the origin is the whole ball of radius H over R, the closure of that ball. And if you're at not at the origin, it's just 1 point. So Alexandrov proved many years ago that the set of subsets of omega where the normal, the subdifferential of E is Lebesgue measurable is a sigma algebra, and he defined the set function M of U is the measure of that set. Measure of E is called the Manjampia measure associated with U. So he was able to introduce this measure. By the way, this predates, this is an early precursor of optimal transportation. These ideas of Alexandrov. So if U is C2 and convex, the Manjampia measure of E, set E is just the integral over E of determinant of the Hessian. So let me show you, I want to give you an example. I see I'm in danger of going over time, so you might have to stand up and stop me. Let me give you an ingenious application to prove the isoparametric inequality by Javier Cabré. He was one of Louis' terrific students. He says, given omega, you want to prove the isoparametric inequality in omega. And let's make it easy, assume omega is smooth. So solve this problem. Solve the Neumann problem. Laplacian U equal 1 in omega. Normal derivative equal constant. So in order to solve that problem, you have to choose the constant by compatibility. If you just integrate, the constant has to be measure omega over measure boundary omega. So if you just use the divergence theorem, yeah, that's what C has to be. And we don't care about translation. So claim the normal map du of the context set contains a ball of radius C. Why? So you have this solution. Suppose you bring a plane. So here's the geometric argument. You bring a plane. So you have this this U, whatever it is, solution of the Neumann problem. And I want to say that if you bring a plane, so what is it? What does this statement mean? It means it means that the slopes of size less than or equal less than C are good slopes. They contact in the interior. Why? So what is a bad slope? If you move a plane, So you move a plane from below, what the contact set, you take the planes, you go till you're well below the surface and you start translating them up. And this has slope P. And suppose that plane contacts at the boundary and not in the interior. So this is a bad slope. A bad slope, oops. A bad slope is one that contacts at the boundary. That's a bad slope. Well, it's easy to see that a bad slope has to, at this contact point, if it's at the boundary, that the size of P must be bigger than gradient U, must be bigger than or equal to C, because the normal derivative is C. So that means that if I take absolute P less than C, that has to be a good slope and contact in the interior. So that's that. This is this statement. The normal map contains this C. So that means that omega n C to the n. So the Manjampia measure of this set, of the contact set, is the integral over the contact set of determinant of the Hessian. That has to be bigger than or equal to omega n C to the n. On the other hand, on the contact set, Hessian U is positive, non-negative. So I can use arithmetic geometric mean. So that's less than or equal to Laplacian U over n to the n. Laplacian U is 1, and just estimate that by the total measure of, so you get omega n C to the n less than or equal to 1 over n to the n, measure omega. And that's exactly the sharp isoperimetric inequality, and you can unravel the equality case to be a ball. So although this idea appears very simple, there's a lot of substance there. I also want to explain just, maybe I'll skip this part. So I'm running out of time, I see. I was going to explain one of the other applications of this idea is a measure, what's called nowadays Alexandrov, Bachelman-Pucci maximum principle. Here's a simplified form of it, just so I don't get too complicated. So take an equation like Laplacian U plus C of XU greater than or equal to 0, and U is less than or equal to 0 on the boundary. And I don't assume any sign about C. So C can be arbitrary sign. And then, so you'd like to say when is the solution less than or equal to 0 in the domain. So normally that's false. So you can use this maximum principle of Alexandrov is really a measure theoretic maximum principle using the same ideas. You can show that if there's a positive constant, so that if the measure of the domain is small, then U is in fact less than or equal to 0 in the domain. Okay, so you don't have to assume diameter, but just measure, and that's important. That's crucial for this these applications. I should also say this is crucial in these ideas are crucial in the proof of Krylov's Harnack inequality and fully nonlinear elliptic equations. So I'm not going to give talk about that. This the papers of Louis and his collaborators have had inspired many other types of symmetry papers, moving plane versions. For example, with Caffarelli and Guidas, we proved a measure theoretic version that allows you to prove asymptotic symmetry. There's Yanyan Li and Manjampia introduced method of moving spheres, which is important for conformally invariant equations. Student of Louis had other extensions, many papers. So let me move on to the Manjampia boundary value problem. So the Manjampia equation is the prototypical fully nonlinear equation. It occurs already in the geometric problems in the Weil and Minkowski problem, many physical problems. When is it elliptic? If you linearize it, you find that the linearization acting on a function is is Aij, Phi, where Aij is the cofactor matrix of Uij. So ellipticity, you don't always have ellipticity on arbitrary functions. You need that Aij to be positive, which is equivalent to U being convex. So this is elliptic only on convex functions. And the Manjampia boundary value problem, which was worked on intensively by the Russian school, Louis and Jean Calabi, Pogorelov. Fine. So the boundary value problem, and of course, there's a complex analog and complex geometry, complex Manjampia, which I'm not talking about. Terminant of the Hessian is a function psi of xu greater than or equal gradient u, which should be positive function, and u has some boundary data on boundary omega. And so the question is, when do you have, if everything's smooth, do you have a smooth solution up to the boundary? Also, okay, so as I said, Pogorelov showed using a famous estimate of his, C2 estimate, interior estimate, and work of Alexandrov, that there's an Alexandrov solution. He was able to prove, use Calabi's ingenious third derivative estimates to prove that there's a solution. If you take boundary data 0, he was able to prove there's a solution which is smooth in the interior with no statement about the boundary data. Louis at the 74 International Congress in Vancouver announced joint work with Calabi, announcing a proof of the general theorem, but there was a gap in this argument, and I think it was pointed out by Chern. So Louis did not give up. So when Louis hired Louis Caffarelli, recognized his great talent and brought him to Courant in 1982. And I was also there at the time, and we started working on this problem that Louis would not give up on. Independently, Nikolai Krylov also proved what's now a classical existence theorem. This theorem says that if you have a strictly convex domain, everything's smooth. If you just want to consider a right-hand side which depends only on x, that's all you need. On the other hand, for general psi, which depends on, for example, if you're considering the problem of Gauss curvature, where this is a curvature equation, then you need some other condition. It's very easy to see that. So the other condition is that you assume for the boundary data, there's a strictly convex subsolution, U lower bar. A subsolution means that you have inequality and it attains the boundary data. Then the theorem was that there's a strictly convex smooth up to the boundary solution. So there are many essential difficulties, but to name two of them, in the continuity method, which we used, you have to show that all second derivatives, the step is to show all second derivatives are bounded at the boundary. Now, if you can, so the tangential derivatives come for free from the boundary data. So then you have to estimate, you have to find an estimate for the mixed normal tangential derivatives. So that's one difficulty. But then how do you find the so the first difficulty is, how do you find the pure normal derivative, pure second normal derivative? Well, the way you always do that is, in all elliptic theory, is to use the equation. So for a uniformly elliptic equation, you can just solve for the second normal derivative because its coefficient, ANN, is uniformly positive. Here, you can write the equation in terms of cofactors, and then you get in a suitable frame, you get ANN, UNN is order 1, where this is the cofactor matrix. So what is ANN? ANN, for example, in the special case, for example, when phi is 0, this boils down to showing that the normal derivative is strictly bounded below, where En is the outer normal. So this is not obvious even in the case of phi equals 0, let alone arbitrary data. Another major problem is that C2F estimates are not enough because the equation is fully nonlinear. You need C2 alpha estimates. So this is the major problem. Even if you can get C2 estimates, how do you get C2 alpha estimates to make the method work? It could break down. This was estimates in the interior can be gotten by either using Calabi's third derivative estimates or famous estimates of Evans and Krylov interior estimates. But you need a new idea. I worked on, I came back to this problem some years later in 1991 because my geometry friends, when I spent the year in Paris, were interested not so much in PDE, but in geometric problems. So the problem they posed to me was, suppose you take, so this problem comes from minimal surface theory, where you consider strictly convex curves in parallel planes. Say you take the plane at height 1 and the plane at height 0, and take two strictly convex curves. So in general, let's consider, so in general, you take two parallel planes, take strictly convex curves sitting in parallel planes. And then, is there a surface of constant Gauss curvature spanning? It should be of an annulus. Is there an annulus of constant Gauss curvature spanning this? So is there something? Of course, you might have to take the curvature small. Let's specialize so we can compare to the classical theorem. Suppose the picture looks like this, where you have the convex curves, they project nicely so that they project onto an annulus. So now I have a Manjampia equation in an annulus. Omega now is an annulus. You have nice boundary conditions, 1 on the outer boundary, 0 on the inner boundary. You have this Manjampia equation. Classical theorem doesn't apply because the domain is an annulus. On the other hand, I went through our argument. The inner boundary poses no problem at all, it turns out. So paradoxically, the inner boundary, which is the non-convex boundary to the interior, poses no. So this suggested, this geometric point of view suggested that there, and Herman knows this very well, suggested that there was a really a better theorem available. And I eventually proved this with my student Boguan. So we proved, in fact, that if you just assume, so of course this problem is not always well posed, but to make it well posed, you assume that there is for the boundary data, there's a strictly convex subsolution, U lower bar. That's necessary condition if there's going to be a solution. And that's all you need. If there's a subsolution, then there's a smooth. If there's a C2 subsolution, convex subsolution, then there's a smooth solution. So this turns out to be, and then you can generalize this to all complex Manjampia, many situations. And it gives a very powerful geometric theorem, and you don't even have to consider graphs. You can actually do this parametrically, but I won't talk about that. The last thing I wanted to say, I'm already 2 minutes over time, is that Louis realized that Manjampia was just the beginning of the story. One should really consider implicitly defined fully nonlinear PDE. Namely, if you have a symmetric matrix, n by n matrix, or maybe a tensor, an important tensor on a Riemannian manifold, define a nonlinear operator f of a to be f of lambda 1 lambda n, where the lambdas are the eigenvalues of a. And then if f of lambda is symmetric, then f of a will actually be smooth. And then if a is, for example, when f of a is determinant of the Hessian, f of lambda is the product of the lambda i's, we recover Manjampia. But this opens up a new world of implicitly defined PDE. When is it elliptic? It's elliptic. It turns out that it's elliptic if f sub lambda I is positive for all I. And f should be concave in order to make it a doable problem in terms of elliptic regularity theory. Louis, I don't have time. Louis realized that natural examples come from Garding's theory of hyperbolic polynomials. There's a nice paper of Reese Harvey and Blaine Lawson that you can look at. This theory turns out to be very important in many contexts. The sigma k's, typical examples are, if you start with this example sigma n, you see that sigma k to the 1 over k are nice examples of f's. So you can consider, but there are also natural examples related to sigma k, like quotients of sigma k over L. So I'm sorry, I don't have time to talk about all these, but we solved a version of this, but people have been working on this, especially in complex geometry, for the last more than 30 years, and there's been substantial improvements. So I'm running over time, so let me just end with some final thoughts. So I think this work on that Louis suggested on fully nonlinear equations, especially implicitly defined ones, unleashed a tidal wave of research in nonlinear PDE and geometric analysis and curvature flows, conformal geometry, complex geometry. So Louis was also, I want to mention, a great PhD advisor. He had 46 students and mentored, I can't tell you how many young mathematicians, including me. And this is all, I think, part of his legacy. He was a very generous, open person and loved to collaborate. And that's something we can all take to heart in our work. He was a consummate New Yorker and a funny, very funny guy. And maybe we'll have time to talk about that. So let me end.